All right, hello and good afternoon. Welcome to Wednesday, day before Thanksgiving. So our Thanksgiving break starts tomorrow, officially. If you're watching live. All right. So we've been talking about hybridization. Whoops. There we go. And that is a topic that will continue to dominate our discussion, at least through most of today. Oops. Hey Richard, what's up? It's good to see you. So yeah, we're talking about hybridization. Just a recap, I guess, of what we talked about on Monday. So we laid out the need for hybridization, that there was a gap between our knowledge of the atomic orbitals, right, holding the electrons around each atom, and the shapes, the VSEPR shapes and geometries that we had been learning, and that with the atomic orbitals, you couldn't explain the bond angles that we observe and that VSEPR predicts. And so hybridization kind of bridges that gap and found a way to use orbitals to explain what we were observing in nature. And on Monday, we were talking about specifically Sp2 hybridization, and how the every atom that has a tetrahedral, every atom with a tetrahedral electronic geometry is Sp2 hybridized. All right. Okay, here. Sorry, hang on one second. I'm picking up some feedback through my mic. I'm just gonna let my kids in the next room know they have a friend over for a sleepover, because they're all on Thanksgiving break. I'm just gonna let them know that I'm streaming. Hang on one sec. Dudes, just a reminder, if you could whisper, that would be awesome. All right. Part of the ongoing reality of having to teach from home is we're not the only people in our classroom. It's low key whoever my mic can pick up. All right, so Sp2 hybridization is the hybridization that every atom with a tetrahedral electronic geometry has. All right, and so we saw what happened. We saw that Sp2 hybridization kind of arose when 1s and 3p. Oops, hang on. There we go. 1s and 3p orbitals are combined / averaged together. All right, this is what happens, or the type of hybridization when we combine our s orbital and 3p orbitals all together to make a new form of hybrid, and that explains the tetrahedral electronic geometry. The question is, what other geometries can we explain with the with this concept, with this idea of hybridization? All right, and the answer is, well, we're going to look specifically at Sp2 hybridization and Sp hybridization are the ones that we're going to focus in on. So let's talk about what happens when we only hybridize 2 out of our 3 p orbitals, all right? What happens then? So let's to kind of highlight Sp2 hybridization, kind of see it in real life. We're going to go ahead and look at the molecule C2H4. All right. Now, if you draw out the Lewis structure for C2H4, I'm just going to do this quickly. Of course, you can do it by adding all the electrons up and whatnot. But this is what the Lewis structure of C2H4 looks like. All right. And this is our first example of with a double bond. All right. Now, to explain, now we can look at each carbon atom and ask, okay, how many electron groups does each one have? And when you look at that first carbon, it has 3 atoms attached to it, directly to that carbon, right? So this would have the geometry trigonal planar. All right, it has a trigonal planar geometry because 3 atoms, no lone pairs, directly attached to that carbon. And actually, when you look at this carbon, you see the same thing, that it has 3 atoms directly attached to it. And when you have 3 electron groups around your atom, it'll have a trigonal planar geometry. So if we actually wanted to draw a 3-dimensional representation of this molecule, excuse me, it would look like so. All right, it would actually look like this. So all the bonds would be in the same plane. All right, and they're each, our bond angles here are 120 degrees. So far, no new information, right? This is all Vesper theory. The question is, how does hybridization and valence bond theory use orbitals to explain this phenomenon? All right, and the way it does is with excuse me, Sp2 hybridization. So remember, we have an s orbital and 3 p orbitals. There's pz, or sorry, there's px, oops, py, and pz. All right, px, py, and pz. Now for this hybridization, what we're going to do, I'm just going to scoot this down. There we go. For this hybridization, we are only going to combine, whoops, our s orbital with 2 other p orbitals, all right? So we are going to take an average of these 3, and what we're going to get out the other end is 3, because we are hybridizing 1 s together with 2 p's. We're going to get 3 new hybrid orbitals, and these are called Sp2 hybrids. All right, we get 3 Sp2 hybrid orbitals out the other end. And if you're wondering what happens to Pz, the answer is nothing. Pz remains unchanged. It was not used in the hybridization process. It's still there. It's just hanging out as an unhybridized p orbital. All right. If we want to talk about S and P character, we would say, because it's 1/3 S and 2/3 P, that these hybrid orbitals are 33% have 33% S character and 67% P character. All right, that those are the percentages. So it's still largely P, but there is a greater amount of S character than in the Sp2 hybrid orbitals. The physical difference, how they look, is pretty much the same. So you'll notice that my Sp2 hybrid orbitals basically look like the Sp3s, but just, if anything, if you were to be accurate, the kind of circular bulge would be a little bit larger because they have more S character than the Sp3 hybrids do. In addition, there's one other critical piece of information, and this will come into play later, and that is the Sp2's the Sp2 hybrid orbital's directionality. With the Sp3 hybrid orbitals, we saw that those orbitals were made from the S orbital, which has no directionality, plus Px, Py, and Pz, right? All three axes were involved. Now, with the Sp2 hybrids, the only orbitals that were used to make them that have directionality are Px and Py, and as a result, the Sp2 hybrid orbitals are all in the xy plane. All right, they're not spread over 3 dimensions, they're evenly spread out over 2, and that's where the bond angles of 120 degrees come from, because they're evenly spread over a 2-dimensional plane, so that's 360 degrees. All right, so these are Sp2 hybrid orbitals. If you were to draw a carbon atom, oops, did not mean for that to come out yellow. It would have all 3 of its orbitals would be, of its Sp2 hybrid orbitals would be within the same plane. So they're all contained in a flat 2-dimensional plane. All right, this is the Sp2 orbitals on carbon. Now let's go ahead and use what we know here let's use the Sp2 hybridization and what we learned about creating bonds, about bonding and orbital overlap, to show how this molecule of C2H4, which is called ethylene, comes together and how those bonds form. All right, let's clear a little space. So first off, we have our carbon atom, and we have our actually I want to draw these in blue. Our Sp2 hybrid orbitals, each with 1 electron. There's 1 electron. Oops, that's kind of a sloppy. 1 electron up in there. Then we have our third Sp2 hybrid orbital. I'm actually going to scoot this down just a tad. All right, now when we look at the Lewis structure, right, for this molecule, and again, let me bust that out right here. we have 2 single bonds to hydrogen. So hydrogen is going to roll in with its 1s orbital and overlap with the sp2 hybrid to create a hydrogen carbon sigma bond. All right, so that is a hydrogen carbon sigma bond, and it's going to do this twice because we see that there are 2 carbon hydrogen sigmas in this molecule. All right, now when you look at this carbon, right, this one right here, it's got 2 hydrogen carbon sigma bonds, and then it's bonded to another carbon atom. So we got to roll in with our second sp2 hybridized carbon. All right, now this atom has the same hybridization as the first, and it is going to create direct orbital overlap to make a carbon-carbon sigma bond here. All right, so this is the carbon-carbon sigma. It also has 1 electron in each of the other sp2 hybrids, and these are going to overlap with 1s orbitals on hydrogen to give us 2 carbon-hydrogen sigma bonds on our second carbon. All right. So at this moment in time, you'll notice that we have drawn out, at least, if you look at the number of sigma bonds in this structure, we have 5 sigma bonds drawn so far. But one of the things you'll notice about our Lewis structure is we have 6 bonds total. All right, we've drawn 5 sigma bonds. We're out of sp2 hybrid orbitals, but there's a 6th bond in this molecule, right? What is that second bond in the carbon-carbon double that we see in this structure? To answer that, it's going to be easier to show what happens here if we rotate the two-dimensional Lewis structure that I have drawn right here. So if we rotate it, so right now it's flat, I'm going to rotate it 90 degrees so that the carbon-hydrogen bonds are coming out of the board at you and then into the board away from you. So I'm just going to redraw this structure here, rotated 90 degrees. All right. So instead of everything being in the plane, the carbon-hydrogen sigmas are coming out at you and going back away from you. Sorry, that's a little ugly. There we go. Okay. So let's take a look. Now, at this point in time, so I'm going to redraw what I have going on here. And at this moment in time, I'm just going to draw my carbon-hydrogen sigma bonds as wedges and dashes because it's going to make it easier to look at, and I really want to focus on how that second bond in the double bond is formed. I am going to draw out, oops, sorry, my carbon-carbon sigma, like so. All right, so there's my carbon-carbon sigma bond. The question is, how does that second bond form? What is that second bond? And what's cool, as you'll see, is it is a new type of bond. Now, let's ask ourselves, what orbitals do we have available to use for making bonds that we haven't used yet? All right, and the answer to that question is we have our unhybridized PZ orbitals. They have not been used to form any kind of bond. All right? The problem here is there is no way for these p orbitals to engage in direct orbital overlap. They can't form a sigma because there's no way for these two, they're parallel, vertical in space, right? There's no way for these two to overlap to make a sigma bond. It can't happen. So sigma bond's off the table. What isn't off the table here is something that's called indirect orbital overlap. All right, indirect orbital overlap. What happens when you have indirect orbital overlap? I'm going to redraw this over here. Indirect orbital overlap happens when you have two unhybridized p orbitals that are parallel to each other in space. All right? They're parallel to each other in space. Something very special happens. They can engage in indirect orbital overlap. And what that is the two lobes on top start blurring together and the two lobes on the bottom start blurring together. All right? They start blurring together to make a new type of orbital and a new type of bond. All right? The bottom two lobes blur together to make one giant blob. The top two lobes blur together to make a blob. And it allows the two electrons to meet in the middle once they've kind of conjoined and become one new orbital. So this indirect orbital overlap right here leads to the formation of what we call a pi bond. Now, something that I want to be very clear about. A pi bond has two lobes. So this is not two pi bonds together. This is one pi bond. There's two halves of it. All right? And the electrons are in the pi bond. And they're blipping up and down between the top and the bottom layers. It's not like they're only on the top or they're only on the bottom. They're moving, shuttling back and forth between the two. This is something now what's really cool about this situation, because often students are like, well, where are they? Are they at the top and the bottom, or the bottom? And with all of these orbitals, the shapes that we're drawing we draw these shapes because electrons are moving super fast. They're like sonic, and when they move, they just create this blur. So the blur of the electron motion kind of looks like it fills both of these spaces. So they kind of both look like they're there simultaneously. And the electron, these are called lobes of the orbitals. There's the upper lobe and the bottom lobe. And the electron is bouncing back and forth between them without traveling the distance in between. It's literally teleporting from the top lobe to the bottom lobe. It doesn't move through the space. It just goes blip, 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 blip. This is a quantum phenomenon called tunneling, and it's super cool. It's tunneling is totally possible, so teleportation by proxy is possible. It happens all the time with electrons, and the distance able to be traveled and the size is partially determined by the mass of the particle. So before the sci-fi enthusiasts get too excited about tunneling and teleportation being real, the largest particle that we've ever seen engage in the quantum phenomenon of tunneling is a proton. So it doesn't get very big. That's and the instances under which protons do engage in tunneling is relatively rare. So electrons can do it all the time, but something as quote unquote big as a proton, which is still very small, rarely does it, but it's still possible. So anyways, I think that's kind of cool. Let's talk a little bit about the pi bond. All right, so it has two lobes. The electrons are both in the top and the bottom. Something. So here, let's just open a new slide. So first off, yep. Okay, that's exactly it. It's like the pi bond is like the top and bottom of a hamburger bun. So pi bonds have two lobes. Whoops. So that isn't two pi bonds. That's just one pi bond, two lobes, and something that's have two lobes. The electrons occupy the top and bottom. I don't want you to I drew them in the top lobe because the top lobe is not shaded, so it's easier to see the electrons, but I don't want you to make the mistake of thinking, oh, they're only in the top. They're both in the top and the bottom. And then it's important to realize that a pi bond is not a double bond. All right? One double bond is one sigma and one pi together. All right? It's a really common misconception to think that, oh, double bonds are pi bonds. Not true. Double bonds are a sigma in between the two nuclei with a pi bond layered above and below it simultaneously. So if we blip back to the previous slide, this right here, this right here is the carbon-carbon double. C double bond C is sigma CC, the carbon-carbon sigma, plus the carbon-carbon pi. All right, it's those two together. That's what makes a double bond. So kind of going full circle. We have 6 total bonds, 5 of them are sigma bonds, 1 of them is a pi bond. All right, and that is what is going on in Sp2 hybridization. Everything with an electronic geometry of a trigonal planar electronic geometry is Sp2 hybridized. All right, the last kind of hybridization type that we're going to dig into in this detail is Sp hybridization, and we are going to look at Sp hybridization with the molecule C2H2. All right, now this is this molecule, the name of this molecule is, you might look at it and go, oh, that's dicarbon dihydride. You wouldn't be wrong, but the official name of it is acetylene, or I should say the organic name is acetylene. And when you draw it out, acetylene looks like so. So it's C2H2, and you have a carbon-carbon triple bond. Now, this molecule, the way we're going to explain, so this molecule, the carbons have a linear geometry, right, Vesper geometry, and we're going to explain this phenomenon with a new type of hybridization called Sp hybridization. Now here, in Sp hybridization, we are only going to hybridize the s orbital together with py. All right, hybridize s and py together, and we get two sp hybrid orbitals when we do this. All right, so these are sp hybrid orbitals. One thing that you'll notice is because we used one s orbital and one p orbital, that these orbitals have 50% s character, um, 50% s character, and 50% p character. And in addition, the only directionality here, that these hybrid orbitals inherit, all of their directionality comes from py, which means that they are both oriented on the y-axis. We saw with Sp3, it was in all three dimensions. Sp2, we lost a dimension, right? It was only oriented in the xy plane. This one, we've lost another dimension because we're only using one p orbital, so it's all oriented in a line on the y-axis. That's why it has a linear geometry. Now, again, if you're wondering, there are two atomic orbitals that we did not use for our hybridization, and those are px and pz. So we still have those two orbitals in play. An unhybridized px orbital and an unhybridized pz orbital that we can use to form bonds, to engage in bonding. All right, now let's take a look how this plays out when we start looking at the orbital overlaps for this molecule. Well, first we have carbon. Whoops. Let's open a new slide. So our carbons are sp hybridized, and their sp hybrid orbitals are oriented along the y-axis. There's one electron in each. All right. Now, for the hydrogens, I'm going to use yellow. Whoops. We get direct orbital overlap between hydrogen and carbon. That makes the hydrogen-carbon sigma. And then the second sigma bond that this carbon forms is with another carbon atom. So here we get direct orbital overlap between two carbon atoms, making a carbon-carbon sigma bond. Followed by direct orbital overlap with a hydrogen atom to make the second. Now, you'll notice in this example, it's similar to the last one, where we have, if you look at our molecule, we have a total of, oops, there we go. we have a total of, let's see, 1, 2, 3, 4, 5. We've got 5 bonds. But here in this structure, as drawn, we only have 3 sigmas. So, and we know there needs to be 2 more bonds, and we're making multiple bonds here. And so you may be suspecting that we're going to have pi bonds involved, and you're 100% on the money. If you draw in your PZ orbitals, right? They're directly above and beneath the 2 carbon atoms. They are perfectly poised to engage in indirect orbital overlap, right? So the 2 lobes blur into each other to make that new type of orbital, that pi orbital, allowing us to form a pi bond. So we blur together above and below the sigma bonds. The electrons are able to meet in the middle, and then we shade one of our 2 lobes. All right, so there's another bond. We've made a pi bond. The problem is now we have 3 sigma bonds and 1 pi bond, but that's still only 4, and we have 5 bonds total in the molecule, so where is the 5th bond? And the answer lies in px. Now, here's what you have to remember. So we've used our 2 sp hybrid orbitals. We've used pz. The only orbital left is px, and px is the hardest one to draw because it comes out of the board away from you, or towards you, and then into the board or screen away from you. All right. Now, admittedly, this is the hardest to draw for any of you who are taking notes in pen. This is where the pencil people will have an advantage. Because the thing is, the px orbital for the first carbon comes out of the board and then back into the board. So this lobe is out in front of all of this stuff, and the beauty of Photoshop is I can erase at will. Those of you writing in pencil can do the same. If you're in pen, you're in a little bit of a bind. So there's 1 px orbital. Let's draw the second one. It's coming out like this, and then going back behind. And again, I'm going to use my eraser to kind of clean this up to make it look more visually correct. And I apologize for the sloppiness of the lines. I promise that I have more motor coordination than a 5-year-old. It's just I'm drawing on a surface. These things are great for doing anything but fine art. Anything visual with drawing other than fine art, these are amazing machines. If you want to do some fine art, though, you want to go with something else. As you can see by the wobbliness of these lines. I'm going to be totally honest. This part's kind of hard for me because I'm not like an amazing artist or anything, but I am really good at drawing orbitals. If we were doing this in class, you'd see I draw some great orbitals, and whenever I draw them on the surface, they always look like wobbly, like I stink at it, which is probably good. It's a humbling experience, right? So anyways, that is px on each carbon. Now what happens here, except again the difference is it's going out of the board at you and then back into the board. What happens here is the exact same thing that happens with our unhybridized PZ orbitals. We have indirect orbital overlap, except with PZ, it's in the plane of the board or screen. With PX, it's like this, all right? But the same thing happens. We blur, this time, out in front, and then back behind. And again, I'm going to use the eraser to kind of clean these up. This allows, so we make a second pi bond and a second pi orbital. This allows the electrons to meet in the middle. One of these two lobes needs to be shaded. I'm just going to use, just want to emphasize that that shaded lobe is behind this. Throw that there. All right. That's about as good as we're going to get it. So this is the three-dimensional picture of the bonding orbitals in the molecule of acetylene. And now we have the correct number of bonds, right? We have 5 bonds total. And we see that there are 3 sigma and 2 pi, all right? This brings home the fact that one triple bond is 1 sigma together with 2 pi bonds. All right, one triple bond is 1 sigma together with 2 pi. The electrons in the sigma are sandwiched between the 2 nuclei. The electrons in the pi bonds are floating above and below the sigma bond, and then to each side, kind of flanking each sigma bond. And that is what is happening when you have a triple bond. All right. Now, we're not quite done with Sp hybridization. There's one last example that I want to share with you. Let's take a look at the molecule C. Whoops. New slide. C3H4. All right. If you draw the Lewis structure out for this molecule. Kate, great question. Kate, great question. Let's talk about the shading just for a minute here. So when you look at any p orbital, every p orbital looks like this. It has 2 lobes with opposite shading. And the reason why the shading is opposite, so the shading is something called phasing. So an s orbital doesn't have any phasing; it's all one phase. But p orbitals and d orbitals have 2 different phases, and it comes from the actual differential equation that you solve to find the orbital solution from quantum mechanics. And it reflects the fact that for all of the solutions, for example, for this p orbital, half of them come out as positive and half of them come out as negative. So it reflects the sign of the solution. So half is positive, half is negative, and that's where phasing comes from. And it actually is important once you get a little deeper into quantum mechanics, because you can have what's called constructive orbital overlap and destructive orbital overlap, and the type of overlap that you get is determined by the phase. All right, so the shading represents the phasing, and the phasing is half of your solutions to the probability density function are positive values and half of them are negative values. They all reflect a place, a location that the electron could be, and there's additional information included in that positive and negative sign that I'm not ready to delve into just yet. So that's where it comes from in the p orbital. And because a pi bond is kind of derived from the mixing of two p orbitals, because a pi bond comes from the indirect overlap of one p orbital with another p orbital. Once they merge to become the pi bond, because the two p orbitals had one half with clear phasing and one half with shaded phasing, once they merge, the lobe that came from the shaded phase remains shaded, and then the lobe that came from the unshaded phase remains unshaded. So that's why you'll notice with all of my pi bonds, I shade one half. Kate, you are so welcome. Thank you for asking a great question. I guarantee you're not the only one who's wondering that. All right, so that's where the shading, the phasing comes from. All right, let's talk about this molecule. If you draw the Lewis structure, it'll come out looking like this. You'll have a carbon double bonded to a carbon, and then the two carbons on the ends will have two hydrogens single bonded to them. All right. Now, let's stop for a minute and assign the hybridization to every carbon in this atom. All right, let's assign our hybridization. First to this carbon. One thing you'll notice is, so hybridization, we began this discussion of hybridization on Monday, and I said that the hybridization is determined by the electronic geometry. So if I point to an atom and ask you to tell me the hybridization of that atom, all you have to do is count the number of electron groups that atom has, and it'll tell you the hybridization. That will tell you. So this carbon has 3 atoms attached to it, no lone pairs. 3 atoms is trigonal planar. That means we have 3 orbitals involved in our hybridization, so that would make it Sp2, 1s, 2p orbitals, all involved in hybridization. All right, 3. And if you look at the carbon on the other terminus, it's exactly the same. 3 atoms attached, no lone pairs. If you look at the atom in the center, the carbon in the center, there's only 2 atoms attached to it, no lone pairs. So that would give you a linear Vesper geometry. Linear Vesper geometries are Sp hybridized. So if we wanted to draw a 3-dimensional representation of this molecule, our central carbon is Sp hybridized, which means it has a linear geometry. So that means it needs to have a bond angle of 180 degrees, right? So we draw it as a straight line. If you look at our terminal carbons, they're Sp2 hybridized trigonal planar geometry. That means they need to have bond angles of 120 degrees. Right? Everything's in the same plane. 120 degrees. Here, let's look at this one here. And here, again, same deal. It's Sp2 hybridized, so its bond angles will be 120 degrees. Now, here's the crazy thing. So we've just drawn a 3-dimensional representation of this molecule based on what we know about Vesper geometries, bond angles, and hybridization, all that stuff. This drawing, this 3-dimensional drawing, right here, this 3D representation, is incorrect. this is not how this molecule looks in 3 dimensions. And we can use our knowledge of direct and indirect orbital overlap to draw the actual picture, to see what this molecule actually looks like in 3 dimensions, and to learn why this is wrong. This is why this is not the way this molecule looks. All right? And that's what we're going to do right now. So let's take a look. First, let's start by, so again, I'm just going to redraw my Lewis structure up here. So that we can have that for reference. And let's start with the leftmost terminus. All right, let's start by drawing our central carbon bonding. Well, here, sorry. Let's start with our central carbon. Start with our central carbon. We said that our central carbon is sp hybridized, right? That means it has 2 sp hybrid orbitals. And it's going to make direct sigma bonds to the carbons both on the right and to the left. Let's start with the carbon on the left. So this carbon is sp2 hybridized. It's going to make a sigma bond with that central carbon through direct orbital overlap, like so. And then it's going to form two more sigmas with hydrogens on wedges and dashes. Right, so these hydrogen atoms are going to come in, making carbon hydrogen sigmas. I'm going to scoot this over. I keep running out of room. That should be enough. All right, and there are our carbon hydrogen sigmas. Now we need to handle the carbon-carbon pi bond, right? And we know how this is going to go down. We know that we have an unhybridized p orbital on each carbon, right? pz. It's in the plane of the board, up and down. And that this will blur both below and above the carbon-carbon sigma to form our pi orbital and subsequently our pi bonds. That looks weird. I'm gonna just redraw my electrons. Okay. So there, we've taken care of our left side of the molecule. Now let's draw the right side. First, let's focus on the carbon-carbon system. So this carbon, also sp2 hybridized. We're going to do direct orbital overlap to form that carbon-carbon sigma, just like we did on this side, right? Those are in blue. But now let's talk about the carbon-carbon pi bond. The carbon on the very right cannot use px to form the new pi bond because the carbon in the center has already used px. Px on that central carbon is already bonding to the carbon on the left. The only orbital left unused for our carbon in the center is its unhybridized px orbital. All right? It's its unhybridized px orbital. And because to form that second carbon-carbon pi, we need indirect orbital overlap. That means that the only bond we can use, the only orbital we can use to make that bond is a px orbital. It's a px orbital on our second carbon. That is how you get the indirect orbital overlap to form our second pi bond. All right, now just cleaning things up a little bit. The eraser, these two electrons, once the p orbitals blend, are free to meet in the middle. We get the two lobes of the second pi bond here in green. Now here's the effect that has on carbon number 2. We know that all of the sigma bonds in an sp2 hybridized atom are in one plane. But for the second carbon on the right, the pi bond is coming out of the plane at us, which means that all of the sigma bonds are in the plane of the screen. So the sigma bonds here between carbon and hydrogen, are not wedged or dashed. They're in the plane of the screen. All right, so the remaining two carbon-hydrogen sigma bonds come in here and here. That means the true three-dimensional depiction of this molecule will have the carbon on the right with all three bonds in plane, but then the carbon on the very left will have its hydrogens wedged and dashed. And this is, all the bond angles were correct that we originally drew. These are still 120 degrees. All right? And these are still 180. But the carbon-hydrogen sigma bonds are not all in the same plane, because in order to form the two pi bonds, the central carbon makes one pi bond with pz and one pi bond with px, and those are perpendicular to each other. This is, right here, the correct three-dimensional representation of C3H4, which the name of this molecule is allene. All right. Okay, so that is the structure and the three-dimensional representation for allene. Now, I want to take a moment. So we're here. We're winding down. We're kind of at the end of our discussion of hybridization, and I want to recap what I laid out for us at the beginning of this discussion. So here's kind of like the big picture take-home message. And really what you want to remember is each atom's each atom's hybridization is determined by its electronic geometry. All right. Each atom's hybridization is determined by its electronic geometry. And the thing to remember here is that, so electronic geometry is going to be Eg, and then the hybridization. All right, and the reason why this is the electronic geometry tells you the number of orbitals you need to hybridize in order to form that structure, really. So if your electronic geometry is linear, and again, it's not molecular geometry, it's electronic. Your hybridization, linear has 2 electron groups, so you're going to use 2 orbitals. It'll be sp. If you're trigonal planar, you need to use 3 orbitals, so it's sp2. If you're tetrahedral, we're using 3 orbitals, sp3. If it's trigonal bipyramidal, then you're using 5 orbitals, so it's sp3d in our hybridization. And then if you are octahedral, then it's sp3d2 is your hybridization. So it's the number of electron groups dictates the number of orbitals you use when you hybridize. All right? Okay. Let's take a look here. All right. So with our last, let's see. Okay, so here, sorry, hang on. I've got to ask my kids to be a little quieter. You dudes, I'm picking you up on the mics. Could you please whisper? So, did you hear me, Vic? Okay, Joshua and Sos, you guys please whisper while I'm almost done with class, but I got another 20 minutes. All right, sorry about that. Okay, so with our last so the end of lecture here, we're going to introduce something called molecular orbital theory. All right, molecular orbital theory. You'll recall that when we started talking about Lewis structures, I said we were going to restrict our discussion of Lewis structures, drawing Lewis structures, with restrict them to the main group. We said that Lewis theory was very powerful, as a great introduction to bonding, thinking about how molecules form, but that Lewis theory could not explain the types of bonding we saw in the transition metals, in the D block, and that another theory had to be developed to explain the reactivity that we saw in that region of the periodic table, and that theory is molecular orbital theory. So this is the theory that had the ability to explain not just what we saw in the main group, but also in the transition block. Now, are we going to get to the transition block with our discussion of molecular orbital theory? The answer is no. I'm going to give you, and because this is all the book gives you, just the very basic, the very introductory form of molecular orbital theory. But I want to tell you at the start of it, this is a much more powerful explanatory method, and it is consistent. It does hold up with the reactivity and bonding systems we see, not just in the main group, but also the D block. So the applications for MO theory are far wider than what we're going to get to in this class, because this is an introductory course. But if this stuff interests you, take advanced upper division organic chemistry, take inorganic chemistry, and you'll see kind of this theory and its ability to explain the phenomenon we see bloom. All right, so that's all sales pitch. Let's start talking about what molecular orbital theory actually is. All right. Now, I want you to recall something from hybridization. All right, recall something from hybridization. We got our hybrid orbitals, for example. We got Sp2 hybrid orbitals by taking our 1s orbital and our 3p orbitals. There I am adding my phasing. And taking an average of sorts, right? And this gave us, oops, that looks a little too much like a p orbital. Let's start from scratch. All right. We got 4 Sp2 hybrid orbitals out the other end, right? We got 4 Sp2 hybrid orbitals out the other end. This process right here has a name, and this is called orbital mixing. All right, orbital mixing. And in orbital mixing, when you mix 4 orbitals, you make 4 new orbitals. All right? You mix 4 orbitals, you make 4 orbitals. That's how orbital mixing works. Funny story, you've been doing more orbital mixing than you know. All right? For example, let's talk about the bonding in H2. All right, if I asked you, okay, can you use orbitals and direct overlap to explain the bonding we see in a molecule of H2, which has one single bond, right? One sigma bond. Of course you can, right? You know how this works. You've got your 1 hydrogen with an electron in its 1s orbital. And then you have your 2nd hydrogen with its electron in its 1s orbital. And what you do is you move these two together so that you get direct orbital overlap between the 2 hydrogens, and that forms, so this is, again, right here, direct orbital overlap. And that makes a sigma bond, right? Now we have one sigma bond. Right there, between the two hydrogens. Funny story. Orbital overlap. Every time you do orbital overlap to form a bond, whether it's direct or indirect, orbital overlap is orbital mixing. Alright, that's why I said you've been doing more orbital mixing than you know. Right? Every time you've drawn two orbitals in direct orbital overlap with each other, you're mixing two orbitals. But wait a minute. I just said that every time the way orbital mixing works is if you mix four orbitals together, you make four new orbitals. And let me ask you, with this molecule of H2, how many 1s orbitals did you mix together to make this new sigma bond? 2. How many new orbitals do you see? 1, right? Just the one that has the electrons in it with the sigma bond. So the question is, if we mixed two orbitals, if we mixed two 1s orbitals, where's the second? Yeah. Where's the second one? The answer to that question is slightly disturbing. Turns out that every time we've formed a bond, we've also created a second orbital. An evil doppelganger. Every time we've made an orbital, every time we've formed a bond, we've made a bonding orbital. But simultaneously with that bonding orbital, we've also generated what's known as an anti-bonding orbital. Putting electrons in a bonding orbital has the strength to hold two atoms together because you formed a bond. Anti-bonding orbitals, when you put electrons into those, you break the bond, you destroy bonds. So we have just been looking at the positive thing, but we have been generating an anti-bonding orbital for every bonding orbital that we've made. And that is the fundamental premise to molecular orbital theory. It's looking at the full picture, not just the orbitals made that are used for bonding, but what about these ones that are kind of the equal and opposite of all the orbitals we've been looking at, the bonding orbitals. All right, and here is, to describe molecular orbital theory, we need to introduce ourselves to something called a molecular orbital diagram. So let's take a look at an MO diagram. Now, in a molecular orbital diagram, you have just one y-axis with energy. All right, so this is right here. Energy on the y-axis. All right. Now, in molecular orbital theory, orbitals are represented by lines. And so this would be the 1s orbital, on each hydrogen. All right, and in a molecular orbital diagram, you don't draw this part that I'm about to draw right here. You don't actually draw this in an MO diagram, but I'm just kind of using it to illustrate the regions of it. These two lines represent the hydrogens these H's are too far apart to bond. They're too far from each other to bond. All right, that's what's going on right here. They're too far. Richard, well said. I have I've got two stepkids. One's 12 and one's 10, and my wife and I recently, maybe about a month ago, we watched The Sixth Sense with them, and the look on their faces when you realize at the end that Bruce Willis was dead was priceless. Nobody does twists like M. Night, in my opinion. And it was fun, kind of experience it, living through it with someone who didn't know it was coming. So these two in this MO diagram, when they're separated on the kind of two extremes, they're too far apart to bond. And what happens in an MO diagram is this central region right here. This is where the atoms, in this case they're hydrogens, the H's have moved close enough to bond. And the question is, what happens to the orbitals as they mix? What are the orbitals that are created as a result? All right, and we have only been looking at the bonding orbitals that form. All right, when you mix a 1s orbital together with a 1s orbital together, we know that you make a sigma bond. Right, and the sigma bond is lower in energy than the individual s orbitals because it's sandwiched in, it's smashed in between the two nuclei. So the sigma bond is formed kind of totally. The sigma bond is formed when you smush those two 1s orbitals together in phase. All right, that's the sigma bond. The antibonding orbital is formed. It's called, the antibonding orbital is higher in energy. So here, I guess, hang on, I should add my H's. Here, hang on, I gotta redraw this. So the sigma bond is sandwiched between the two nuclei, and it's formed when you have the two 1s orbitals in phase, and it's kind of smushed in between there. The antibonding orbital is higher in energy, and it is called the sigma star antibonding orbital. And it looks like so. You have your two hydrogen atoms. The sigma star antibonding orbital has two lobes, and they are located behind each hydrogen atom, and they are out of phase with each other. So the sigma star has a lobe right between the two nuclei, which is stable, low in energy. Sorry, the sigma does. The sigma star, it's out behind the two nuclei, and it's what happens when you mix your s orbitals when they're out of phase. When they're the same phase, it's constructive orbital overlap, makes a bonding orbital. When they're out of phase, it's destructive orbital overlap, then it makes an antibonding orbital. All right, now the way that you show that the sigma star and sigma bonds come from mixing these two 1s orbitals together is you draw a dotted line from the atomic orbitals to the molecular orbitals that you form. So these out here, so that is the that is how you construct a molecular orbital diagram. Conceptually, these are what all the regions represent. What I'm going to do now, I know we're 1 minute over. I'm going to finish with the molecular orbital diagram of H2, and then we'll pick this conversation up on Monday. But I just want to complete the MO diagram for H2. So here's how the molecular orbital diagram works. So we have sigma, our sigma bond down here, sigma star up top. You've got to show the dots connecting each molecular orbital, which is sigma and sigma star, to the atomic orbitals that you mix to create them. All right, and then you write in the electrons held in each atomic orbital. The 1s orbital for hydrogen has 1 electron. So we put 1 electron in each. And then when you mix these two orbitals together, those electrons you have to house within your new molecular orbitals, all right? So you have to take these electrons, you have to place in your new orbitals. And as we know, electrons always go for the lowest energy orbital available. Sigma is lower energy than sigma star, so both of these electrons are going to occupy the bonding orbitals. So we show that by drawing them there. Both electrons are in the sigma bonding orbital, and there are no electrons in the anti-bonding orbital. The last thing that we're going to touch on today is something called bond order. All right, bond order. Bond order, you calculate bond order by taking the number of electrons, or here, I'm going to write this vertically. You can calculate bond order by taking the number of electrons in bonding orbitals minus the number of electrons in antibonding orbitals. All right, you take that difference and then you divide. You take whatever that answer is and divide it by 2, and that's your bond order. So if we were to calculate our bond order here for H2, we have 2 electrons in antibonding orbitals. We have 2 electrons in bonding orbitals, 0 electrons in antibonding orbitals. Divide by 2, that gives you a bond order of 1, i.e. a single bond. All right, and if you look at the Lewis structure for hydrogen, it does have a bond order of 1. And if you're suspecting, you're like, wait a minute, is a bond order of 2 a double bond and a bond order of 3 a triple bond? The answer is yes. All right, so bond order is something that you kind of already know, but it's a way of, it's a part of molecular orbital theory, and you calculate it by taking the difference between the antibonding orbitals and the bonding orbitals in your molecular orbital diagram. Now, there's a lot more that we're going to do with this. We'll pick it up on Monday. I want to leave you with a question. And you can You can ponder this question over Thanksgiving. We'll pick up with this question on Monday. And if you're dying to know the answer, you can always drop by office hours, which we will still have tonight. But here's the question. Have you ever wondered why does the molecule H2 exist, but the molecule HE2 does not? Have you ever wondered that? If you have, I'll tell you how you can find your answer. Draw the MO diagram for dihelium and calculate the bond order. See what you come up with. And we will pick up there in office hours not in office hours, in lecture on Monday. If I don't see you in office hours, have an awesome Thanksgiving. Stay safe. Be thankful. And I'll catch you all